So now we're going to look at bonding and structure, another fundamental topic in chemistry, whether you're doing GCSE, A-level, university level, or whatever. So, first type of bonding, very important, ionic. Now, as soon as you think, what's an ion is an atom that is charged. Of course, we see that there are some more complicated ions that can be molecules that are charged because it has gained or lost electrons. And let's just think back. I'm going to take a nice simple one. Lithium. Lithium, element number 3. It's got 3 protons in the middle. It's got 3 electrons arranged in 2 shells. Now, it's got 3 protons. It's got 3 electrons, 3 minuses. It's going to lose that outer electron so that it ends up with a full outer shell. The nucleus hasn't changed. It's still 3+. The outer shell electron has been lost. That shell is no longer there. It's got a plus charge. Why? Well, it's still got 3 pluses in the middle, but it's only got 2 minuses around it, orbiting the electrons. So it's got a positive charge. So if you lose electrons, you become positive. Non-metals. So let's take fluorine. Actually, I'll just draw its nucleus, is element number 9, so its nucleus is 9+. It's got 9 electrons around it in total. 2 in the first shell, 7 in the second. It wants 1 more to get a full outer shell. So the electron that lithium gave away is going to go to there. And so we'll end up, bear in mind, lithium's got 9 pluses, 9 protons, and 9 electrons. Fluorine is now going to have, still got 9 pluses in the nucleus never changes, but now it's gained an electron, 9 pluses, it's got 10 electrons, because it's gained 1, so it's got a minus charge. And really, that's all there is to it. And now you've got something with a positive charge, something with a negative charge. What is ionic bonding? It is the electrostatic attraction between oppositely charged ions. And some people get muddled up with metal, non-metal, 2 non-metals. Is it ionic or is it covalent? Look, you've got your periodic table in the exam. Metals on the left, non-metals on the right. There's a zigzag line there dividing them. Now, this is pretty easy to remember. Metals on the left, non-metals on the right. Okay? So, we've got lithium. I've given the example of lithium reacting with fluorine. Lithium on the left, group 1 metal. Fluorine on the right, non-metal. It's going to be ionic bonding. Think about them. Metals and non-metals are opposites. So how are they going to bond? They're going to be bonding by making oppositely charged ions. So don't forget that. Crucial. Whenever you get your periodic table, you're asked about a compound of 2 elements, you must immediately know whether it's ionic or the other covalent. So that was ionic bonding. Now let's just think covalent. What if non-metals are allowed to react with other non-metals? So let's say we've got hydrogen, element number 1, and we've got fluorine again. I'll draw it with all its electrons first of all, but from now on I'm only going to draw out a shell. 2 non-metals, they both want to gain electrons, because non-metals gain electrons when they combine. They both want to gain electrons. How can they both gain electrons? How can fluorine gain an electron and hydrogen gain an electron? There's only one way they can do that, and that is by sharing their outermost electrons. I'm only going to draw the outer shell. Those 2 are meant to be overlapping. They share electrons. Whenever we're drawing covalent dot cross diagrams, I like to draw the shells as well as the electrons. At A level, you don't have to draw the shells. They will accept diagrams like this, but personally, I prefer to see the shells drawn. With more complicated molecules, it certainly makes things a bit easier to see, I think. Okay, so that's covalent bonding, and at GCSE you might learn it's sharing a pair of electrons. Just remember, for the moment, you'll get a different definition at A level, but it's sharing, and it's always a pair of electrons, or 2 pairs, or 3 pairs. Electrons love being in pairs. You'll find out why at A level. And it's always 2 non-metals. I'm saying it's always 2 non-metals, and I said ionic was always a metal and a non-metal. You discover exceptions. Of course there are exceptions. That's what makes chemistry A-level, I think, really interesting. Not every element is as predictable as you might think. And there are compounds at A-level you find which is a metal and a non-metal, but turns out to be covalent. There are compounds that are 2 non-metals that turn out to be ionic. And you've touched on that at GCSE when you've looked at acids dissociating into ions. But we'll come back to that in another video. Okay, so that's covalent bonding. And the other important things you need to know about the types of bonding is the properties. Properties of ionic and covalent compounds. I've had to zoom out here because here's the smallest model I've got of a crystal of salt, NaCl, where silver represents a sodium atom, green represents sodium ion, beg your pardon, green represents a chloride ion. And they form what we call a giant lattice. A lattice is just a repeating pattern of, in this case, oppositely charged ions, and it repeats many, many million times over. So 1 grain of salt might be 1 million ions by a million, something like that. A huge number of ions together to form our lattice. And because there are millions of these bonds holding the ions together, and because the electrostatic attraction of oppositely charged ions is strong, this thing is going to have a high melting point. It's going to take a lot of energy to break all those electrostatic attractions. So that's the first thing we need to remember. Ionic bonding, high melting point. The second thing is, when it's a solid, of course, the ions are fixed in place. They can vibrate a bit, which this model doesn't represent. They can vibrate a bit, but they can't move around. So when it's a solid, they cannot conduct electricity. But when it's a liquid, and you can make it a liquid in 2 ways. You could melt it by heating it up to 800 or 900 degrees, or you could simply dissolve it in water. When your ionic compound is a liquid, the ions can move around. Positives can go towards negative electrodes, negative ions can go towards positive electrodes. So when it's in liquid form, it can conduct electricity. So that's your ionic compound, always forms a giant lattice, high melting point, only conducts when in liquid form. Then there's your giant covalent. And here's an example. This is diamond. And in diamond, every carbon atom, remember, diamond is a pure form of carbon, every carbon atom forms 4 bonds, except for the ones on the edges. And that 3-dimensional structure of 4 bonds is actually like the perfect structure. Bonds that are short tend to be stronger. Carbon has small atoms, therefore short bonds. And it forms 4 bonds at just the right angle to one another. So it's kind of like the perfect structure. 4 strong bonds to atoms above and below, making the hardest known substance, the strongest, if you like, substance known to mankind, your diamond. Now, of course, because of all those strong covalent bonds, it has a very, very high melting point. And because all the electrons in the outer shells of the carbon are being shared between atoms, there are no electrons left over to move around. Equally, there are no ions. There's no positive and negative particles separate from one another. All the electrons are around the outer shells of all the atoms. There's no way that can conduct electricity. Then let's take a much simpler covalent molecule. This represents water. We've got oxygen, 2 hydrogens. Now, these grey bonds represent covalent bonds. It's probably not the best example. This one's a bit better. Covalent bonds are strong. That's why diamond is so hard. and has such a high melting point. Covalent bonds are strong. If you put water into a kettle and you boil it, you don't break covalent bonds. They're far too strong to break even at 100 degrees. However, water boils. It boils very easily, unlike carbon that does not. So, what's the difference? Well, basically, it's down to this idea of a simple molecule. Only 3 atoms as opposed to trillions of atoms. Those 3 atoms stay together very strongly, they bond very strongly, they're a very stable entity, but they don't particularly attract other molecules very strongly. In fact, I'm going to do it like that because that's a better representation. The blue tack holding these 2 molecules together represents weak intermolecular forces. And if I give a molecule a bit of energy, and I didn't even need to give it any extra energy there, if I give it a bit of energy, make it move around a bit, the intermolecular force breaks very, very easily. If you ever find yourself at GCSE or at A-level writing strong intermolecular forces, you're probably not going to get the mark because no intermolecular forces are strong. Some are stronger than others, but most are very weak, okay? So yes, some are stronger than others, but none of them are actually strong, okay? Intermolecular forces tend to be much, much weaker than covalent bonds. I can give that molecule a shake and they come apart, but it doesn't matter how much I shake it, the covalent bonds don't break because they're much, much stronger. So, in summary then, our properties. And we need to know this and be able to explain it. Ionic compounds, they form this giant lattice. They have a high melting point, boiling point, because they're strong. I'll just write bonds here, but electrostatic attraction between oppositely charged ions takes lots of energy to overcome. So it's going to be a high temperature. Also, they only conduct when liquid, i.e. molten or dissolved in water. Covalent, 2 types of covalent structures. There's your giant, like our diamond. Again, high melting point, boiling point, takes lots of energy. Again, to break all those covalent bonds because covalent bonds are strong. And then we've got simple covalent. We're talking about things like water, low melting point, boiling point. Why? Because they've got weak intermolecular forces. We do much more at A-level about the nature of what are these intermolecular forces, because it's not obvious why there should be anything between one molecule and another. When I put that bit of blue tack there, why anything at all? But we do that at A-level. And because they have weak intermolecular forces, very little energy needed to overcome them. And giant or simple, they tend to be non-conductors. There are no free charges, delocalized electrons, or ions to move around, non-conductors. We come across the exception to that rule, which is graphite. I won't go into that there. Okay? So, that is our ionic and covalent 2 types. The last type of structure, which we don't do in very great detail, is just metallic, where the outer shell electrons of each atom become delocalized, so you end up with metal ions, and it's only the outer shell electrons that become delocalized, and you end up with a lattice of positive ions, and in between you've got your electrons whizzing around so fast they're just a blur. The electrons of that atom do not have to be there, they could be over there. The atoms spread out. In fact, they spread out and they move so fast, they are literally a blur. They're more of a wave of charge rather than particles, but we won't worry about that too much. And again, usually these forces of attraction between the positive ions and the delocalized electrons are strong, usually. But of course, you know group 1 metals melt quite easily. And they conduct electricity, of course, because the delocalized electrons can move around. So that's pretty much everything you need to know before you start A-level on bonding and structure.